Good evening, everyone. I'm Ninad Gaikwad, a PhD candidate in the Mechanical and Aerospace Engineering Department at University of Florida. I'll be presenting my paper titled Smart Home Energy Management System for Power System Resiliency, co-authored with my colleague Narendraman Shrivats and advisor Dr. Ravi Barua. In the recent past, it has been observed that the frequency of extreme weather events like hurricanes, tropical thunderstorms, and blizzards has increased. The powerful winds associated during these events have been responsible for the damage of transmission and distribution system of the power grid, leading to extended power outages. For residential consumers, extended power outages result in rotting food in the refrigerator, thermal discomfort, and no lights at night, effectively reducing their standard of living to the level of 19th century. Is there a way to provide resiliency to the residential consumers during such an outage? Hence, our goal is to provide reliable energy supply to a house for maintaining habitable conditions during extended power outages at reduced cost. The most common solution is using a diesel generator. However, there is a recurring fuel cost along with air and noise pollution. If we decide to reduce our carbon footprint, then the next viable solution is a PV battery system. However, with the basic control system it comes with, it is incapable of making optimal decisions in order for the system to not die. As a result, a large system size has to be installed for reliability guarantees, which in turn increases initial capital cost. We propose that with an intelligent controller, a smaller PV battery system can provide reliable power during these extended power outages. In order to measure the economics of the two controllers, that is, the baseline and the proposed controller, 6 different system sizes of the PV battery system were simulated with the same simulation setup. The measure for resiliency was chosen to be the refrigerator temperature violations above a desired maximum, which is represented by the y-axis on the figure to the left. The red dots and the blue triangles in the figure represent the baseline and the proposed controller's resiliency performance against system size. It is quite clear from the figure that a proposed controller with half the system size as that of the baseline controller provides the same level of resiliency performance, effectively reducing cost by half. What can intelligence exploit? It is a pertinent question at this point. To answer it, let us first have a look at the system. It consists of a house installed with PV modules and a battery storage unit. The electrical loads considered within the house are refrigerator for storing and keeping food items fresh. This is considered to be a critical primary load. Lights for providing illumination at night and fans for providing thermal comfort. Both of these together are considered to be critical secondary loads. Now, we have flexibility in generation as excess PV potential can be stored in the battery and be used when there is no solar energy or less of solar energy. Also, there is a flexibility in the battery charging rate so that it can be charged either in a fast or normal charging mode. However, fast charging degrades battery life. Finally, there is flexibility in demand as the primary critical load, that is the refrigerator, has a high priority over secondary critical loads, that is the lights and fans. All these different flexibilities provide an opportunity which can be exploited by an intelligent controller to meet the desired goals. However, a simple rule-based controller which accompanies the current residential PV battery systems is incapable of utilizing these flexibilities, as more sophisticated mathematical construction of the problem is required for the same. During the literature review, we came across Prince et al. 2019, which was the only relevant piece of work similar to ours, which shows the lack of focus of the controls community in general towards this problem. However, it ignores the mixed integer nature of the problem arising out of all decisions to be made for the electrical loads, and it did not consider the flexibility in battery charging rate. We have accounted for both these caveats in our proposed controller. We will be looking at two controllers, the proposed controller, which is an MPC-based controller with a mixed integer linear program, and a baseline controller, which encapsulates the rule-based controller logic of the currently installed residential PV battery systems. The figure illustrates the baseline controller schematic. We can see that it comprises of two controllers, the battery logic controller and the refrigerator deadpan controller, which act independently of each other. These controllers are rule-based. The battery logic controller requires the information of current time step PV energy potential and the house load demand to create the current time step charging discharging control commands. The refrigerator deadpan controller requires the current time step refrigerator internal temperature to create the current time step refrigerator on-off control command. Here we see that refrigerator deadpan controller turns the refrigerator on when the internal refrigerator temperature goes beyond the allowed maximum. It turns it off when the internal refrigerator temperature goes below the allowed minimum, and otherwise uses the previous control command. Now, looking at the battery logic controller, we can see that it creates the charging command when the PV energy potential is greater than the house load demand, and creates the discharging command when the PV energy potential is less than the house load demand. Also, both the charging and discharging commands are complementary. The figure illustrates the proposed controller schematic. This is a model predictive controller with a mixed integer linear program. Hence, we have state feedback, which in this case are the refrigerator internal temperature and the battery state of charge. The other information required by this controller is forecast of the energy generated from the PV panels, hence a PV energy model is required, predictions of the internal house temperatures, which require a house thermodynamics model, and the demand trajectories of the secondary critical house loads, which are lights and fans. All this information is required for the entire planning horizon. Also, in order for making energy forecasts and house temperature predictions from the PV energy model and the house thermodynamics model respectively, weather forecasts are required for the entire planning horizon. The output of the controller are the control decisions for charging discharging status of the battery, battery charging mode either fast or normal, and on-off status of the primary and secondary critical loads. Let us look at the MILP problem formulation. The following equation is the cost function which tries to minimize the refrigerator temperature slack, to keep the refrigerator temperature within desired bounds. It tries to maximize the battery state of charge so that the PV panels are used at their maximum potential and the system has optimal energy stored to supply for house load demand. It tries to minimize the battery charging rate to avoid fast charging where possible and as a consequence reduce battery degradation. And it finally tries to maximize the secondary critical load control command to optimize the secondary critical load servicing. Let us now take a closer look at the first term of the cost function. The lambda is a scalar weight which is heuristically tuned to obtain desired response. The n-k term is time index dependent constant weight, and the rationale behind it is that we care about the objective being met in the early part of the time horizon as compared to the latter part of the time horizon. The zeta FR variable is the refrigerator temperature slack variable, which takes positive values once the refrigerator temperature goes beyond its desired maximum, as can be seen in the figure to the lower right. This avoids infeasibility. The remaining three terms of the cost function have also been designed with similar rationale. The constraints for the MILP problem include the linear dynamic constraints of the refrigerator thermal dynamics and the battery storage dynamics. The energy balance constraint provides for the generation demand equilibrium. The refrigerator temperature is bound between desired minimum and maximum. The refrigerator temperature slack is introduced to avoid infeasibilities and by construction needs to be non-negative. The battery state of charge is bounded between the maximum and minimum battery energy capacity. The battery charging and discharging rate is bounded between an appropriate lower and upper bound so that it can provide for discharging and both the modes of charging. The secondary critical load control command is bounded below by 0 and above by 0 unless the secondary critical load demand trajectory is positive. This reduces the degrees of freedom for the secondary critical load control command but improves performance. And finally, the solar energy production variable is bounded below by 0 as production cannot be negative and bounded above by maximum energy potential of the PV. The implementation of the primary and secondary critical load control commands is straightforward, as the proposed controller provides binary control commands which can be directly used to control a smart switch. However, the implementation of battery control command is not straightforward, as the battery charging discharging rate variable is continuous and it has to be converted into discrete control commands using the illustrated rule-based logic. A one-week simulation is conducted starting on the day Hurricane Irma had its landfall in Gainesville, Florida in 2017. The weather data is obtained from the National Solar Radiation Database. The PV battery system size is 1 kilowatt and 5.4 kilowatt hour respectively, and the house has one refrigerator, 6 LEDs, one each for every room in the house, and 4 fans, one each for every bedroom in the house. For the MILP computation, a planning horizon of 24 hours at 10 minutes resolution is used, resulting in 144 time steps in the planning horizon. This MILP is solved with Gurobi solver on a desktop Linux computer with 8 GB RAM and 3.6 GHz octa-core processor. The figure illustrates the secondary critical load demand trajectory for a 24-hour period, which is constant for each day of the 1-week simulation period. This trajectory is user-defined. In our case, the user desires lights to be on during the evening and the fans to be on during the night. The figure below illustrates the primary critical load performance for both the controllers. The plots in blue and red represent refrigerator temperature for the proposed and baseline controllers respectively. We can see that the proposed controller is able to maintain the refrigerator temperature within pounds throughout the simulation, which avoids rotting of food. The baseline controller on an average causes 7 hours per day of refrigerator temperature violation above the desired maximum, which according to the CDC guidelines is 3 hours higher than required for food safety, which will definitely cause food to rot. The figure below illustrates the battery SoC performance for both the controllers. The plots in blue and red represent the battery SoC for the proposed and baseline controllers respectively. In case of the battery SoC, the period for which it stays at its minimum value is considerably negligible for the proposed controller. That is, practically battery never dies. Moreover, the usage of the fast charging mode by the proposed controller is seen when battery SoC peaks are compared with that of the baseline controller. The figures below illustrate the secondary critical load performance for both the controllers. The plots in black are the desired secondary load demand trajectory, and the plots in blue and red are the service secondary critical load demand for the proposed and the baseline controllers respectively. The proposed controller serves the desired secondary load demand 9% times more compared to the baseline controller. This performance superiority of the proposed controller is attributed to the information it consumes in terms of forecasts and predictions, and making trade-off between conflicting requirements as solving an optimization problem. As we saw in slide number 5, in order to measure the economics of the two controllers, 6 different sizes of the PV battery system, as shown in the table to the right, were simulated with the same simulation setup. From the figure, we can conclude that the proposed controller with half the system size as that of the baseline controller provides the same level of resiliency performance, effectively reducing cost by a factor of 100%. The MILP optimization problem solves for 1008 decision variables, out of which 288 are binary. This makes it a hard problem to solve. Using Gurobi with 1% optimality cap setting gives an average solver time of 1 minute per MPC iteration. However, the time limit setting had to be used to stop the solver, as this problem can lead to stalling of the solver for certain iterations. With time limits set to 5 minutes, the solver stalled for 7% times of the simulation duration. To summarize, a MILP-based MPC controller has been developed for residential PV battery load system for post-hurricane power outage scenario. Its performance in regards to primary and secondary critical loads has been shown to be superior as compared to a baseline controller through simulations, and this is directly attributable to its ability to exploit the flexibilities in the generation, battery charging rate, and the demand. Finally, its economic benefits have been shown to be 100% more than the baseline through Resiliency Performance study using systems of different sizes. For future work, we need to analyze the proposed controller's sensitivity to forecast errors. There is also a scope for reducing its sensing and forecast requirements. And finally, we need to find a computationally cheaper way to solve MILP-based MPC problems. Thank you.